besides a penny. Yep. Is that all I have?
Yep.
I finally got the ones besides a penny. When did it go? Nice. Four coins. Mendelevium? Which was Mendelevium?
Mendelevium. Alright.
Trivia question, we get a coin. Trivia question. Okay. Oh, trivia question for you. Do you have any pennies? Huh? Yeah. Okay. Give me one of your pennies. Why? I'm gonna show you why. I was just like, how can you use your? Why can't you use your penny? Because none of mine have it. Have what? What years are going? Huh? What years are going? 2011. Oh, that's what they're doing. Is there any other? Why? You're looking. You see, I got $1,000 for one because I have very edge right there. There's an FG. And we have yeah.
Louis, stop giving coin advice. You know nothing.
All right.
There you
Yes. Please say it.
We went to the back. And that way, like. Oh.
Remove your shoes. Freaking cookies.
Did I have
Gonna see what a sigma. What a sigma? What? What a sigma or what a sigma?
What does you need to go find out?
Okay, stop.
We need it. You're not going to wear your shoes inside. Bro, I don't have anything.
Party bag.
Hey, Adriana. Good.
Right here.
Can you take it in the folding table down on the
No.
Yeah. Yeah, but you're gonna help because you're a gentleman. Nice. Not really. I'm gonna pretend like you're a gentleman and you're gonna help. Yeah. No, it's a crazy idea, right? You got.
Where's Archie? Archie, what's back? Back with it. Alright, y'all.
That doesn't go on the floor. That goes straight back to the, and then.
Hi, Bubby. Good, my good boy.
You mean?
Oh,
Play. You nice later.
I think we have to.
Hey, the trees are, look at you. No, thank you, Maude. I told them not to bring outside inside, but I knew you'd be the one to do it. It's your jam.
I think.
I get the space. Get the space.
Oh, what you got?
No.
Well, that, yeah, it doesn't go out. Yeah. That doesn't go in there.
Chair.
Yeah.
And I'll.
Someone's eating my
Yeah.
Well, all right, I appreciate the interesting array of things that arrived today, three-legged chairs and pegboards and whatever. That's all right. That's cool. It's for real cool. All right. All righty, crew. Are we ready? We've all returned from the back 40. It would appear. Come. Okay. All right, so we're gonna start with chemical bonds, and these are light, these next few lessons, right? Because this is really next year's stuff. So we're just touching on it. So we're gonna start with defining what is a chemical bond, and it's the attractive force that holds atoms or ions together. Oh, she's like, huh? What? All right. So we have three main types of chemical bonds. Anybody want to give me what our three main types are? Yusuf? Ionic bonds are the first kind. All right. Anybody want to give me what's the second type that is subdivided, Drew?
Covalent.
Covalent is subdivided into polar and non-polar. And then what else do we have? You look like you know. Hydrogen bonds are between between molecules rather than between atoms. Jordan.
Lattice.
Sort of. So what we're looking for is metallic. That's our last kind. And yes, there are hydrogen bonds, but we'll talk about them. We'll talk about them in a minute. So what's that say? In the purple?
Methylene dioxide.
Methylene, dioxymethamphetamine. Anybody want to guess what it is?
Meth.
Meth, you think? What is meth?
That's not a drug.
Yeah.
Try one day.
What?
Nobody wants to take a guess? That's actually, that's actually that's a recreational chemical. Sometimes not so recreational if it's not given to you intentionally, but that's MDMA or Molly. Yeah, that's what that is. Yeah. Big complicated thing that the people who use it probably have no idea what it is. All right, ionic bonding and ionic compounds. So let's talk about a couple things here. What is a compound composed of ions bound together by electrostatic attraction? PJ?
Ionic bond.
There you go, ionic compound. Yeah, ionic compound. So that is a compound that is composed of ions. Now, so your ionic bonding is going to have obviously ions together. So the collection of atoms corresponding to an ionic compound's formula, such as the molar mass of the formula, is the same as the mass of 1 mole. Does anybody know what this one is? So this one just, I'm throwing it out so you see it. This is formula unit. Okay, it'll come up next year, but I'm tossing it out there so it's at least something you've heard before. What is an ion made of 2 or more atoms? Do we know what that is? Raise the roof. Do you know? Not a molecule. You know? No, those are polyatomic ions. Okay. So what's an isotope again? PJ?
An atom with more or less
Electrons. Not electrons. You had it though.
Neutrons.
Neutrons. That is an isotope. And then what's an ion?
an atom less or more electrons.
Electrons, right? So your ions have less or more electrons, which means they have a charge typically, right? And we have two different types of ions. We have cations and anions, right? What's the positively charged kind, Bailey? Cation, and the anion is your negatively charged, right? Okay, but then you have polyatomic ions, which are ions that are composed of two or more ions put together. So your ions are composed of a metal and a non-metal. What you're often gonna see is one of these two, something in one of these two columns, combined with very often one of these guys here, right? So great example of your probably most commonly known, easy to remember ionic compound is sodium chloride, which is what?
Table salt.
Table salt, right? So you see that you have your sodium over here and then your chlorine over here, and together you get sodium chloride, right? Now you're gonna find that there are endings like "ide," "ate." Yeah, there's all kinds of, and we'll get, next year we'll get into what that means, right? But you'll see a lot of that. They completely transfer electrons, which is stealing or donating. It depends on which atom, which atom you're talking about in the compound. So basically one atom is gonna have an extra, like kind of it's not really extra, but it's like a valence electron that's kind of at an unhappy level, which makes it almost extra to that atom, which we'll talk about in a minute. And you'll see it because I have a graphic that makes sense. But they're not shared, they're completely stolen. And they form ions when they're put in water. They do dissolve and can form ions. Solids at room temperature. So let's think about table salt. Table salt, does it form ions when you put it in water?
Yes.
How do you know?
It transfers electrons.
Yeah.
I put like the copper, zinc. and
Yes.
Paper with salt water.
Yes. So salt water is conductive, right? But regular distilled water, not so conductive, not comparatively at least. Solids at room temperature, is table salt solid at room temperature?
Yes.
Yep. How about a high melting point?
Yes.
So here's a great way to compare your covalent and your ionic bonds. So you can take a crucible, which we'll use a lot next year, but it's a little tiny, like ceramic pot, basically. It's a little itty bitty pot with a little itty bitty lid. And you can put some salt in one crucible and some sugar in another crucible and put them above a Bunsen burner each. And what do you think will happen to the salt if you heat it a lot with the Bunsen burner underneath in a crucible? What's gonna happen?
Soup. Black soup.
The salt would?
No, the sugar.
The sugar becomes soot. So the sugar is going to break down. Those bonds will break with thermal energy, right? So you apply thermal energy, the bonds and the sugar will break. It'll get sticky, gooey, it'll caramelize, then it'll become soot, which is essentially carbon, right? Because it's the carbon in the sugar that's breaking down. And then the other components of the sugar other things happen to them. But the carbon is what you see left behind. How about the salt? What happens when you heat up the salt? Really?
Warm salt.
You get warm salt. That's pretty much it. Yeah, like you just get nice hot salt. Because it's got to melting temperature on those things is really, really high. So their bonds are much, much stronger. Yeah.
But it is possible to melt salt.
Yeah, it's got to be very hot. You're not going to do it in your crucible with your Bunsen burner. Not going to be a thing. They have very strong bonds, like we were just saying. It takes a lot of energy to break them. They're brittle. Is salt brittle? If you squash a little thing of salt, is it going to break or squish? It's going to break, right? Like if you put pressure on it, it's going to crush because it's brittle. It's non-conductive, but when it's in liquid, it releases ions, then it becomes conductive. So if you just try and run electricity through a giant block of halite, big thing of salt, it's not going to happen, right? That doesn't work. But the ions themselves can be conductive. Yes.
Would molten salt still be salty?
I wouldn't taste it. I'll let you be the one.
Yummy, just pour it on your food and you'll
Mhm.
see whether it preserves it properly.
That's what I was thinking. How would you?
You would just disintegrate your face in the process.
Like that?
It's part of the
Like it's
process.
pour it on and cook the steak.
Mhm.
Salty steak.
It keeps. it
Yeah, but that's because it dissolves with the water coming out of the steak. So then they have ionic charges, right? Positive or negative. So I want you to look closely at what's going on. At their top, we have our sodium chloride. That's what we're doing here. Sodium right here is 11. Your first energy level, your first electron shell has two, how many in it? 2, okay? We have something called an octet rule. After you get past that first one, they like to have 8. How many? We got 8 there, right? And then the next one, and then in the third one, how many electrons?
42.
Oh, I'm just asking in that third energy shell in sodium, how many electrons do we have there? It's red. You see it?
One.
In the in the third shell. So the first shell we have 2, second shell we have 8, the third shell we have just 1, right? And that makes sense because here it is over here. So we just have 1. All right, that's not what it wants. It wants 8, but it has 1. So is this going to be easier for sodium to get rid of that extra electron or get 7 more?
Get 7 more.
What do you think? Who says get rid of it entirely? Who says get 7 more? So it's gonna be much easier to get rid of 1 than it is to get 7. But if you look at chlorine, how many electrons are in its third shell? 9. 7. How many does it want?
1.
It wants 1 more. So it wants 1, and sodium is happy to get rid of 1, which is why you get an ionic bond between sodium and calcium. Sodium and chlorine, sorry, sodium and chlorine. It's happy to say, here, steal my electron. It'll make me happy. Take it, please. Get rid of it. So ionic bonding is a force that attracts electrons from one atom to another atom and transfers a neutral atom into an ion. So that sodium it'll become an ion because now what you've done is you've given away 1 negative charge, right? Right. It's got 1 less negative than it's supposed to have. So now it has a charge. An ionic compound is a 3-dimensional network of positive and negative ions mutually attracted to one another. They tend to be harder and more brittle and have higher boiling points than materials containing only covalently bonded atoms. Now, something to keep in mind, it says covalent and molecular compounds. When we talk about compounds that are bound ionically, we tend to just call them compounds or ionic compounds. But when we talk about things that have covalent bonds, that's when we start using the word molecule. People want to say, it kind of gets interchangeably tossed around. You'll hear people refer to all kinds of things as molecules, but in chemistry, we kind of want to reserve that term for covalent bonds, not ionic bonds. Okay. So let's look at a couple of these terms. A group of atoms that are held together by chemical forces. A molecule is the smallest unit of matter that can exist by itself and retain all of the chemical properties. What are these? It is molecules. Ta-da! Okay, so what's the difference between a molecule and an atom when we're talking about smallest unit? Colin?
Molecules are made of 2 or more atoms grouped together.
Yeah, and it says that a molecule is the smallest unit of matter that can exist by itself and retain all of the substance's chemical properties. So compare that to how you define atom. How would you define atom? So what's the difference between Ozzy? What's the difference between an atom and a molecule then? Like you said, there can be multiple different kinds of atoms in a molecule, but why is it saying then that a molecule is the smallest unit of matter that retains all the properties of the matter? James?
Yeah.
You can't, yeah. So think about this. Oxygen, okay, Ozzy, what are you doing over there? He's trying to eat stuff under the table. Come on. So oxygen doesn't like to hang out by itself. It likes to hang out with a buddy. So typically when you see oxygen in the world, you see it as O2, and that is a molecule of oxygen. All right, it's all alone. It's the smallest unit that's going to retain the qualities that make oxygen oxygen. But how about if we put it with 2 hydrogens and we get H2O? We have what? What is it? Water molecule, H2O. Okay, if you break the H2O down into H and O, does it still retain the qualities of water?
No.
No, right. So that's why you have molecules being the smallest unit of matter that retain the qualities of that matter. But atoms being the smallest unit of an element that retain the qualities of that element. Does that make sense? Yeah, kind of, yes.
But couldn't an element also be considered matter? Like if you just had like
Yes.
a giant gas of
Yes,
pure hydrogen, it's
Yeah.
still matter, right?
that's what I'm saying. O2 is oxygen.
But it retains all of the qualities of hydrogen.
Mm-hmm. Yes, you can. So yes, they can be the same thing. If that's what you're asking. Can an element exist as a molecule that is just the element? Yes. Like O2. H2 as well. It's going to usually be by. Mm-hmm. And a molecule can be just that element combined with, itself, like O2. Right? Yeah.
What helium? Helium never bonds.
Yep. So then you just have helium. And that can be considered by itself. It's an element.
Oxygen molecule, just O1, does that not retain the qualities of oxygen?
It does, but you're never going to see it that way in nature, just by itself. All right, so just keep that in mind, the difference between molecules and atoms when you're talking about the simplest unit, right? All right, so a chemical compound whose simplest units are molecules are what we call molecular compounds, right? That's what we're saying. We're comparing molecular compounds with ionic compounds. All right, so a combination of chemical symbols and numbers that represent a substance. What's this called? Well, so this one's your formula, which we're gonna be looking at a bunch of chemical formulas in a minute. And we're gonna be doing some kind of guessing at how to name them because we haven't learned how to name them really yet.
I was balancing them again.
Oh, that's coming next year. Next year, we're gonna be balancing the heck. You're done. Yep. It actually is kind of fun. We do a,
We had to deal with Alex all caffeinated and sugared up.
Yep.
Oh, that's fun.
plus Alex can look at the chemical equation and balance it in his head in about 5.2 seconds before anybody else has even written it down. So there's that. All right, so next thing is a chemical formula that shows the number and kinds of atoms in a molecule, but not the arrangement. So this one is what we're going to call the molecular formula. Okay, so going to be a little different. These are just terms that I'm just introducing you to. Now we've got an electron configuration notation in which only the valence electrons of an atom of a particular element are shown. So this one is an electron dot notation. Okay, in your notes, I think you have Lewis dot, right? So that's our specific type of electron dot, and that's this one right here. So it's a formula in which electrons are represented by dots, dot pairs, or dashes between two atomic symbols, and they represent pairs in covalent bonds. So we're going to look at those in a minute, but I think you had one. Didn't you have one in your notes? Didn't you have a Lewis dot in there? There was definitely a Lewis dot on the lab with the Skittles and M&Ms. Remember you had that little lithium? And I think it showed it as a Lewis dot as well. So how about a formula that indicates the location of atoms, groups, or ions relative to one another in a molecule that indicates the number and location of chemical bonds? Did anybody find this one? Y'all are like, oh my goodness. So this is a structural formula, okay? These are all just things you're going to be exposed to next year. So we're just showing you that they exist. So then you have a covalent bond in which two atoms share one pair of electrons. Does anybody know what this kind of bond is? It's a covalent bond. You have two atoms sharing one pair of electrons. So if I told you this was a single bond, then what do you think it would be when you're sharing two or more pairs? Double bond and triple bond, or two types of multiple bonds. Very good. So it's pairs of electrons that get shared. Do we understand the difference between shared and stolen or donated? So in ionic, they literally, like we were showing in that graphic a minute ago with the sodium chloride, that chlorine is going to like take that other electron. But when you're talking about covalent bonds, they're shared. So you can kind of think of the electrons as cycling back and forth between the two atoms. So that bond is not as strong, which we'll find a lot about next year when we do it. So the bonding in molecules or ions that cannot be correctly represented by a single Lewis structure, this is called resonance. Just be aware, it's a different kind of resonance, not the resonance we studied this year, right? So covalent bonds form between metals and nonmetals. They are sharing of electrons. So this is not stealing or donating like in ionic bonds. They form molecules. They are solid, liquid, or gas at room temperature. solid, liquid, or gas. Whereas ionic at room temperature, what kind of compounds? What kind? Solid, right? Always solid. Low melting and boiling points. And ionic compounds have what kind of melting and boiling? High melting points for your ionic compounds, low for your covalent. Weaker bonds, you can break these apart. If you put, they're soluble in water too, a lot of these too. They're brittle, they're still brittle, soluble in water. Poor conductors, is sugar water gonna be a great conductor of electricity? Not really.
Great snack for hummingbirds.
That's true. Good snack for hummingbirds. And then you've got your polar and your non-polar. So in polar, you have unequal sharing of the electrons, and it ends up that the molecule has a slight charge on one, on one side. Okay, that's the end result. You have a slight charge on one portion of that molecule. And in non-polar, you get no charges and nothing. Yes.
Normally polars have higher melting points
Mhm.
and boiling points than non.
Yes, that's true. So covalent bonding occurs when atoms share one or more pairs. So that's what we're remembering. And a non-polar covalent occurs when electrons are equally attracted to both. And a polar covalent bond occurs when electrons are shared by two atoms, but more closely by one. That's what we just said. Atoms and molecules are joined by covalent bonds. In a covalent bond, two atoms share one or more pairs. And then we have, here's the octet rule. How many, after you get past that first electron shell, how many electrons does an atom want in that shell? Shells 2, 3, 8, right? It wants 8. That's the octet rule, okay? So it likes 8. So if it's like sodium and it's got an, Milo, God, it's got an, that's the last thing I needed to see. Okay. Ozzy's toy over there, Milo's pretending to eat it, but it, yeah. Okay, or maybe I'm not sure what that is. So, talent. Bonding, sorry. Bonding within many molecules and ions can be indicated by Lewis dot structures. All right, well, you know. All right, so let's look at metallic bonds. This is our, excuse me, our third type of bond, right? So what does malleability mean? Jordan.
It's how hard a
Mhm.
object is to break.
Mhm.
To break apart.
That's a good description of it.
Opposite brittle.
Okay, very good. You have another?
The ability to bend an object without breaking.
Bend without breaking, uh-huh.
How squishy it is.
How squishy it is. These are good. Okay, so it's the ability to be, there's also ductility and conductivity. It's the ability of a substance to be hammered or beaten into a sheet. So, how about copper? Is copper malleable? Yeah, you can pound copper into, you can feed it with a hammer into a sheet, right? You can get it into a nice big sheet. They can roll it out. They can do that with steel and aluminum, like your cans are made of, you know, drink cans are made of aluminum, right? So obviously it's malleable. So then what's ductile? Did anybody know what ductile means? PJ, do you know? No? Caitlin, do you know?
How helpful it is to duct tape.
Great question. So yeah, that's a good answer. I like that one. Do you know, Liam?
The ability for water to pass through it.
Not water. That's a good one.
Liquid.
One more guess?
How it can be rolled into like a wire.
There you go. So it's can it be pulled into a wire? Okay. So some metal is great at being hammered into a sheet, but not so great at being pulled into a wire. Copper is a great example of one that does both really well, right? You're probably familiar with, you've seen copper sheets. I'm sure you've seen them like over awnings and stuff. Sometimes people put them as part of their architecture because it's pretty, but you can also pull it into a wire. Copper wire is nice and flexible and very conductive, right? Because we used it in lab this year. So then what is conductivity? We got malleability, ductility. Bailey?
How easily heat/energy can be passed through.
Yes, thermal energy and electrical energy. How well does it conduct thermal and electrical energy? Very, very good. Okay. So a metallic bond is formed by the attraction between positively charged metal ions and the electrons around them. And then you get what's called an electron sea. So they're formed in metallic bonds. They give metals the properties of high electrical and thermal conductivity, malleability, and luster. This is what makes metal metal. So basically you get everything kind of in this lattice, And then all of the electrons are just kind of floating all around in between everything at all times. They're just bumping all around like a sea of electrons. And so that's why they're so conductive. That's why they're so conductive, right? Because you've got so many free electrons that you can access. So then we have other type of bonds. All right, so here's your hydrogen bond that James brought up. So the hydrogen bond is intermolecular. What does intermolecular mean? You can break that down. Jordan.
Is it like subatomic? So like,
That's in, you're thinking intra. If it was intra, it would be inside the atom. Well, or inside the
say it
molecule.
again, sorry.
Intermolecular. What does that mean? Inter.
So,
Do you know, Caitlin?
Like, can be passed through molecules.
That's a good one. That's close. Where does an interstate? Oh, Asher, do you know?
It exists between one.
Between molecules. I was gonna say, what's an interstate do? It goes between states, right? Because it takes you from one state to the next. So intermolecular would be between molecules. So hydrogen bonds, the best example of hydrogen bonds that you see every day are water. Water molecules are bound to one another with hydrogen bonds. This is why when you pour water in a graduated cylinder, you get that meniscus, right? Because there's surface tension, and that's from the hydrogen bonds. Anybody ever seen those bugs that walk on the water? Those oarmen or whatever they are, waterman bugs, they literally walk on the surface tension of the water. Yeah.
I was just thinking, like, if you pour
Mhm.
water into a spoon or something,
Uh-huh.
so that it should be like flowing out, you can see it like bubbling
Over. Yes, that's like the
It just
opposite.
stays there.
Yeah, it's like the opposite shape of that meniscus inside the tube for the graduated cylinder, but that's what you get. Yeah, so we have, again, ionic bonds, covalent bonds, metallic bonds. These are all molecular bonds, right? Or compounds. These are what form compounds. And then, yeah, there's James Bond because he's fun. And then, yeah, there you go. And then your hydrogen bonds are intermolecular. So they're bonding one molecule to another molecule. All right. So here's some other terms to throw out, just so you're familiar and you know they exist. So bond energy, lattice energy, and dipole. Bond energy is the energy required to break the bonds in 1 mole of a chemical compound. Okay, mole. Oh boy. Anybody know what a mole is? Anybody ever heard of a mole? Do you know what a mole is?
Well, it's simply the unit of measurement that you're going to for atoms.
Yeah. Mm-hmm.
The people running the underground
The
government.
people running, and they are there. I believe you. They are 100%. Yeah. So yeah, a mole is it's how we measure atoms, and not how we measure it like the particles within atoms. We were doing AMU, right? Atomic mass units. We were measuring atoms with atomic mass units, and we were measuring the particles, the subatomic particles, using AMUs as well. But a mole is a way to measure a lot of atoms, and we'll do it next year, but there's a number that goes with it and everything, and it's where your scientific notation kicks in and all that fun stuff. Lattice energy. So this is energy associated with constructing crystal lattice relative to the energy of all constituent atoms by infinite distances. Wow, that's a fun thing. We'll talk about that a lot more next year when we do ionic compounds, because those do form a crystal lattice. Anything you see that's crystalline in structure, so salts, quartz, things like that, that's where you're going to find a lot of ionic bonding involved, right? And then a dipole, which you probably could have guessed this, it has positive and negative charge regions. Dipole, polar meaning charge, di meaning two. So VSEPR theory. All right, this is where it gets interesting. Remember our Bohr models. All right, you sat there and you had your Skittles or your M&Ms and a series of circles, and you placed things where they went. It was kind of Russian doll-esque, right? Like you had one energy level and then another one inside of it, another one inside of it, until you get down to the nucleus of the atom. All right, but stop. So what I said is they don't actually look like that, right? The electrons are more, the whole quantum mechanical theory is that they're moving around in these clouds, but the clouds do have shapes. And it's fascinating how they determine the shapes. It's a probability thing. So they look at it and they're like, where am I most likely to find this electron? So it predicts some of the molecular shapes based on the idea that pairs of valence electrons surrounding an atom repel each other. Okay, so there's Vesper theory when you're dealing with molecules, but that has to do with, well, what is the shape of the atom to begin with? Where is that negatively charged particle? Because it's going to repel another negatively charged particle from a different atom within a compound, right? So what you get is, okay, look at this. All right. So this is Vesper theory, and it'll tell you whether molecules are linear, whether they are trigonal, whether they are tetrahedral, pyramidal, bent, linear. So there are all these different shapes. Have you ever seen drawings like this? Like with somebody referring to molecules, you ever seen drawings like this? Sometimes you'll see these. There's also, there are some rings that form. They're like pentagons and hexagons and octagons where you can see the molecules will actually kind of join together and form rings. A lot of organic compounds have that, as well as like really long chains that kind of trail along behind. So here's some Vesper theory, and this is like a memorizing tip, and I won't expect you to memorize it obviously right now, but it's good stuff to kind of show you what we're talking about. And it's short.
Here we talk about chemical bonding. In that, we take PSCPR theory here. And I know you're not able to learn some shapes
Christopher.
of molecules if you're given about the lone pairs and the bond pairs. But I now have a very interesting way that you can learn them very easily. Yes, you will not forget them. See, what you have to do is
Don't forget.
take a table like this, 21, 22, 31, 32, 41, 42, and 51. Now, separate them. These are bond pairs. These are lone pairs. And here we have the shapes. Banked, banked, triangular pyramidal, T-shape, seesaw, square planar,
Square.
and square pyramidal. If you learn about them the way I want you to, then you'll not forget it. Yes.
You'll not forget it.
He comes before everything alphabetically, but you'll say he comes after S, but you just remember beats. Just be everyone, the S
Beats.
and last, okay? Now, for remembering which one comes before in T pyramidal and T shape, go alphabetically. Here we have the P and here is S. Which comes before? Simply P.
So it's a combination of an alphabet and this mnemonic,
In
right?
learning, like
So that's what he did. What he did was this chart right here, basically. He was finding a way to break that down, right? Okay, into something simpler. So now let's talk about charge, all right, and metals. Let's watch this one for a minute. That guy was just real short to show you that there is a quick way to learn that if you care to learn that. You don't need to learn it for your exam.
About how to find the ionic charge for transition metals. So when we find
For
ionic
these
charge,
guys,
with
right?
ionic charge, we often think of the pattern on the periodic table. 1 forms 1 plus ions, 2 plus, and we skip the transition metals. That's what we're interested in this video. But we skip them and we go 3 plus, 4 plus or minus, and 3 minus, 2 minus, 1 minus 0. And that's very useful to understand the general trend for ionic charge on the periodic table. It's a bit of an oversimplification though. If we look at a more detailed periodic table, we'd see that we still have group 1, they're all 1 plus, 2, 2 plus. So here are the transition metals. We have these post-transition metals, some of these down here like lead. So this is a little more detailed, and you'll note that there's really no 4 plus or 4 minus on this table. So here we have 3 transition metals though that always have the same ionic charge. Silver, 1 plus, and then zinc and cadmium, they're always 2 plus. But for the rest of them, some of these transition metals down here, we really don't know what the ionic charge is. To find it, we'll look and see what it's bonded to. So these are all positive. We'll see what they bond to here. And then we can work backwards to determine the ionic charge. So let's try that, see how it looks. Let's try copper oxide. So copper transition metal is right around here. We don't know its charge, but oxygen, you know that oxygen right here has a 2 ionic charge. And this copper oxide, right now, it's neutral. There's no plus or minus out here. So all the charges, they add up to 0. The net charge is 0. Oxygen, 2 minus. That means for them all to add up to 0, the copper has to be 2 plus. And that's its ionic charge. We would say for the name, copper 2 oxide. And the 2 would be a Roman numeral in parentheses after the word copper. So 2 oxide here. Let's try another one, maybe a little more complicated. How about Fe2O3? This is a component of rust. So we don't know what iron is, it's a transition metal, but we do know again that oxygen has that 2 minus charge. So we'll put our 2 minus charge up here. And we know that all the charges on the Fe2O3 compound, they have to add up to 0. So 3 times 2 minus, that's 6 minus. So this part of the compound is 6 minus. So the question is, to get 6 plus, what is the charge on the iron? 2 times something will give us 6 plus. So 2 times 3 plus,
There you go.
that'll give us 6 plus. These will cancel out, they'll add up to 0. So the ionic charge on the iron is 3 plus. We call this iron 3 oxide. And note that this 3 plus, there's 2 iron atoms, so each one is 3 plus. Now you try one. How about CuCl2?
All right, what do we think? Anybody want to give it a try? Cl. Chlorine, right here. So what's the charge on it? -1. Okay, 1 minus. And where's Cu? It's over here somewhere, right?
-2, so it's 2.
2, 2 plus.
Okay, don't forget this guy. So we got it? Y'all think 2 plus? 2 plus is our answer?
For CuCl2, again, copper, that's a transition metal right around here. Chlorine, that's right here. 17, sometimes it's called 7 negative. All of these have the 1 minus ionic charge. Right, 1 minus up here. 2 times 1 minus, that's 2 minus. So the copper, to have this 2 plus, so these add up to 0, has to be 2 plus.
There you go.
Kind of imagine a 1 times 2 plus gives us the 2 plus. Net charge is 0. The charge on copper is 2 plus. We call it copper 2 chloride. Pause and try this one.
Okay, do one more. All right. Fe2S3. So where's our S?
-2.
Yep, 2 minus.
-6, so it's 3. 3 plus.
What does anybody else think? Anybody get anything different than 3? Going with 3?
So for Fe2S3, it's pretty much the same as Fe2O3 because these are in the same group. Overall, neutral compound. So we look up oxygen right there, 2 minus, 3 times 2 minus, so maybe 6 minus. This has to be 6 plus. 2 times 3 plus. That'll give us
There we
6
go.
plus. Net charge is 0. Iron 3 sulfide. We'll wrap up with one more.
One more. All right,
ZnC.
zinc and chlorine. Okay,
2 plus. 2 plus.
anybody want to guess? Yusuf is throwing out his guess. Anybody else have a guess? 3 plus? 2 plus? 2? Sorry. Numbers growing out there.
Again, neutral compound, all the charges add up to 0. Chlorine, that's right here, that has that 1 minus. We have 2 of them, so 2 minus the zinc has to be 2+. But we also know zinc is an exception for the transition metals, it's always 2+. So we could have known that without figuring out the fluorine. If we name this compound, because zinc is always 2+, we could just call it zinc chloride. We don't have to call it zinc 2 chloride. It's just zinc chloride. This is Dr. B with.
Yay, Dr. Whomever. All right, now I got one more and then we're gonna do a guessing game. This is a quick one. And this one's on naming covalent compounds, okay? There's gonna be a lot of naming stuff next year too, and then sometimes that's a challenging
In this
thing.
video, I'd like to talk about writing covalent compound formulas. Covalent compounds are composed of 2 metals. You can find the nonmetals on the right side of the periodic table. Covalent compound formulas use prefixes. The prefixes go like this. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona 9, and deca 10.
Okay, remember
It will
those.
help
You need them in a minute.
Memorize these. Let's get started with a couple.
Those are worth
of
memorizing.
formulas, and I'll go through some of the rules. Up first is CO. Rule number 1, with the first element, if it does not have more than 1, or in other words, if it's just 1, you just say the element. You don't say monocarbon. And then for the second one, you do add the prefix. So this will be carbon monoxide. Up next is N2O. Now we have 2 nitrogens, so we will use a prefix of di. So it will be dinitrogen monoxide, because you only have 1 oxygen. Also notice that instead of all of oxygen for the second term, you use IDE. Next.
That's for
you
these
have
examples, but it's not across the board.
N2O3. So let's put all the rules together. You have dinitrogen because you have 2 nitrogens. And then you have 3 oxygens, so it will be tri, and then you add the IDE. So it would be trioxide, dinitrogen trioxide. Now let's work it the other way. Up first, we have SO2. That will be sulfur, because you only have 1 of those, and it's the element name, so it'll be sulfur. Then you have 2 oxygens, it'll be dioxide. Next, you have PH3.
Anybody want to give it a try? pH3. What's the P? Phosphorus.
Phosphorus,
Hydrogen.
phosphorus,
Phosphorus trioxide.
Phosphorus
hydrogen.
trihydride.
And that will be
Hi,
phosphorus
trihydride.
trihydride.
Yeah.
Also, the first.
And finally, you have CH4, which is carbon tetrahydride. So there we go, naming covalent formulas. Thanks for watching.
All right, now that you see that, we're gonna use it in just a second here. All right, we're gonna guess. You ready? It's not a Menti or anything. This is just, let's take some stabs at them. All right, what is the common name of this chemical? Everybody say it. Hydrogen peroxide. That's right. That's what you call it. If you want it, you want to use some for something, you call it hydrogen peroxide. What's its chemical name though?
Hydrogen peroxide.
You are correct. Hydrogen peroxide. Okay, so what do we think is the chemical compound for hydrogen? The formula, sorry. Do you know?
HO4.
HO4 is a good guess. Do you know?
No, it's
Okay. This one's gonna break the rules a little bit from what you just learned. So this one's an H2O2. So this one doesn't quite fit with the rules that we just had. But yeah, there's a lot of rules. That was like basic step 1 of rules. Okay. But
This is like English.
uh-huh. But you'll see here, some of these are gonna line up with what we just did. Now, what's this common name?
Bleach.
Bleach. All right. Now, what's the chemical name for bleach?
Beach.
Well, Clorox is the brand name. What's the chemical name for bleach? Anybody know?
I was gonna say that.
Chlorine, okay, so this is a good point. It's called Clorox, so Caitlin has a point here, it's called Clorox, so maybe there's chlorine in it.
Chlorine
I did smell
oxide.
Chlorine oxide, something like that. All right, so what you get is sodium perborate. Where's the chlorine in there?
No.
Do we see it?
Right.
Sodium, but where's the chlorine?
Perborate.
There's no chlorine in here.
Yeah.
Why is it called Clorox if there's no chlorine? Because they're dumb.
Sounds like chemically.
I think you're on the right track. I would
like a cleanup.
yes, I think that's it. I think it simply sounds like something you clean with. Yes.
Yeah.
It-
It makes.
I'm not 100% sure behind how Clorox was named. That might be something worth Googling. I bet there's an interesting internet rabbit hole on that, but there's no chlorine in it. So if it's sodium perborate, anybody want to take a stab at what's in it? We know what sodium's in it. So that's what? What's the chemical symbol for sodium?
So,
No, sodium. Na. Na. And what else is going to be in it?
Na2 because it's per.
Okay, Na2 he's suggesting. Okay, and then borate. Boron, very good. You get a boron. That's over. Whoops, sorry, there. I'm like, ready to go. And then when you see 8, it usually is going to mean that you've got like an O3. So a lot of things that have an O3 are going to be the 8. So again, you're like, wait, this doesn't fit the rules. Sodium perborate. What happened to the whole, like, where's the per coming in, right? But that borate, that's right there. So keep in mind that ATE usually means you've got an oxygen attached to something, all right? Now what's this one? Borax, that's its brand name. Anybody want to guess at what chemicals you might find in borax?
Sodium.
Sodium? Boron, somebody say boron? I would guess boron, it's called borax, wouldn't you think? Anybody?
Clorox was obviously
Not chlorine, right? Okay, so its chemical name is, whoa, sodium tetraborate decahydrate. Okay, now, this one you can do. Sodium is what? Na. What would tetraborate be? We just saw perborate and there was a BO3. So
B4.
B4, what do you, anybody, what do you think? BO4, what do you think? 5, okay. And how about decahydrate? 10 what? Hydrogen? What does hydrate mean?
The hydrogen with the O3.
The hydrogen with the O3. Oh, you're thinking, okay,
It's got the ATE at the end.
okay. But the ATE is attached to the borate.
And the deca. It's on both.
Yes, it is. 8. Hydrate.
It was boring. Water?
Water. Okay, so let's have a look.
I think.
N2BO4O7.
I knew it was that.
10 H2O. Decahydrate, 10 H2O. If you saw trihydrate, it would be what? 3 H2O. And that little dot means that those molecules exist together in this compound. Okay, so you've seen something now, you're getting real close. What's this?
Yeah, cheese.
Not cheese.
Chips.
Sulfur?
Higher
If I told you its
Yeah.
common name was
Yeah. Higher food, that's so what?
brimstone.
That snack is goaded.
What's brimstone?
What?
Popcorn?
Oh.
Where have you heard of,
Higher food.
where have you heard of brimstone before?
Minecraft.
Minecraft. A lot of people have gone, but not Minecraft has brimstone. Where else?
Earth science.
Earth science, we had a little brimstone. Anybody heard of like hellfire and brimstone raining down? Like these are like biblical things, like, oh, raining down hellfire and brimstone. Well, what the heck is brimstone? It's sulfur.
Wow.
When you're in Minecraft and you're building with brimstone or whatever you're doing with brimstone, it's sulfur.
Yay.
It does stink. So what's gonna be the chemical formula for brimstone? S, we got it. That's easy. It's just sulfur. It's just straight sulfur. Alrighty, what's this?
Cream of tartar.
Cream of tartar. What do you do with cream of tartar?
McCormick.
Yeah, you do cook with it. What do you put it in?
Like salted.
Oh.
Yeah, meringues.
Hey.
It's necessary in meringues.
The shape.
Oh, did you put that in the,
Mhm.
I put that in the little cookie?
Yeah, the meringue cookies. Yeah, very good.
That you want.
So it keeps things kind of light and fluffy.
What
So,
happens when you put it in ice cream?
It's a cream, it's a cream of tartar. What is tartar? What are we creaming? What is this? Like, what is cream of tartar? Like, what is
73.
73? She says is, oh, that is tantalum.
I can't leave him here.
Yeah, tantalum. So how about if I told you it's because it's potassium hydrogen tartrate, which is a chemical name for something. Tartrate is a name. So now you have to know what tartrate is in order to figure it out. But that cream of tartar is actually taking its name from its chemical name, unlike, you know, like
Fluoride.
most other yeah, and most other things in your kitchen are not taking their name from their chemical name. Like you don't call salt something chloride or something, whatever. You just call it salt, right? So what's in it? Oh boy, there's your potassium, K, your hydrogen, H. So what is tartrate?
Carbon. Hydrogen.
C4, H4O6 is tartrate.
Hey.
That's what it is. C4H4O6. So potassium, hydrogen, tartrate. All right. What's that?
Pencil.
Epsom salts.
Dr. Keels.
Who likes their Epsom salts? I love my Epsom salts. I slide my Lucy butt into the tub with Epsom salts all the time. Makes my life better. Epsom salts are great. Yeah?
Snort them.
Snort them. Let's
Yes.
not snort them ever. No, those are a different kind of bath salts. Those are not, no. Those aren't actually bath salts you're thinking of.
Oh, man.
So what is Epsom salt made of?
Hold on.
What do you think?
Magnesium chloride.
Magnesium chloride?
That's
It
all the
says-
ultrafine
Sodium
crystal.
chloride.
Yeah, it says ultrafine crystal.
Yeah, it is
so
crystals
It
and
has to
salt.
have some kind of crystal.
There.
So it's ionic. Yeah, what do you think? Sodium,
Sodium.
sodium.
Salt.
So he says magnesium and chloride, magnesium chloride.
I saw it on the box.
So he's got it spot on, yeah. Or or it can be a magnesium sulfate. There's different ones. Heptahydrate. Oh, here's something that's gonna help us get. So you know it's a salt, right? Because you have one of these guys and one of these guys. So you got yourself a salt. Heptahydrate. Okay, so what is magnesium sulfate heptahydrate? What are we gonna get chemical formula wise? Mg,
SO.
SO.
Eight.
uh-huh,
H2O.
hydrogen.
7, what was hydrate?
H2O. H2O.
7 waters. So we know we have a 7H2O at the end. So the only thing you need to figure out to get this one is what is sulfate? So there's an O, well, what's our subscript gonna be? And that's where you have to kind of know what's your subscript gonna be. So in this case, it's MgSO4, 7H2O. So PJ was like almost there, real close. But next year, y'all will be doing all these. You'll be able to look at this and be like, oh, I got it. You can write it down. You'll just know how to do it because we'll do it so many times that you'll just know how to do it. Yeah, you just know how to do it.
That doesn't sound like.
All right, what's this one?
Gasoline.
Caitlin?
Helium.
Helium?
Gasoline.
DJ?
That thing for grill.
The thing for grills? Propane? Helium? Propane?
Freon.
It's not helium or propane.
Freon.
Freon.
Yeah.
Where do we use Freon?
Car refrigerant.
That says car refrigerant. So where in your car is it? It's not the coolant for your engine.
AC for us.
It's, yes. So this is what makes your air conditioners make things cold. You need Freon. You ever heard of anybody getting their air conditioner charged?
No.
That's adding Freon to the system typically. Freon is what we use. So its common name is Freon. What do we think is in Freon? Anybody want to guess?
Free and.
Cannot read it.
Hydrogen.
Hydrogen, maybe some hydrogen. What do you think, Xander? I mean, Lucas, sorry.
Carrot.
Carrot. Xander, do you have a guess?
You're not funny.
You haven't guessed yet. I'm looking at who all has guessed.
You beat it as that horse.
You got anything else? Got a hydrogen? He says a hydrogen. Nothing else? You wanna guess anything else? Ridley, you wanna guess? What's in it? We've got a guess for hydrogen.
There are numbers on the box.
Yeah, there's numbers on the box.
134A.
And I don't see a formula though. Milo, you wanna guess? Chloe? Pick an element, any element. What might be in here?
Very common.
Yeah. Otherwise.
Terbium.
What is it?
Neon.
Neon? Okay. Chloe? What's in it? Any guess?
Terbium.
Plutonium.
I'm not sure. Plutonium. Bailey, you gonna guess?
California.
Nitrogen. That's a good guess.
California.
Lucas, you're the only one. No, wait. Xander, you're the only. No, you guessed. Somebody guessed.
Rhodium.
All right, let's see. Here's what's in it. Oh, fluoro, difluoromethane. So what's the first thing in it?
Chlorine.
Chlorine. What's the second thing in it? Fluoride, how many?
2.
Two fluorine. So chlorine, 2 fluorine, and then we gotta know what methane is. Okay, now methane is in and of itself, yeah, a separate chemical that we name. So what you get is CF2Cl2. Ooh, fun times. All right. What's that?
Aluminum.
What is it?
Gallium.
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 Gallium, it would be liquid at room temperature.
Aluminum.
Aluminum. What is it? Zinc? What do you think? Caitlin? No?
Nickel.
I love everybody's guessing. Iron?
Silver.
I was thinking potassium or one of those sodium, one of those metals that
Ah,
react.
the reactive, he's guessing it's one of the reactive ones that you have to store in like mineral oil.
Is it nickel?
So its common name is galena. Yeah, it's not something you hear that commonly, is it? But it's lead 2 sulfide. So what's in it then? Lead and what?
Sulfur.
Lead and sulfur. So you get, public broadcasting station, PBS. There you go. PBS. All right. What's that? Good gracious. What kind of alcohol?
Whiskey.
Grain alcohol, but what?
Grain alcohol.
How, grain alcohol. Okay. What is grain alcohol?
Alcohol made from
Fermented
grain.
It is alcohol made from grain.
The corn.
So compare grain alcohol to any of your other distilled spirits like vodka or rum. What makes this different? You know?
High level.
High.
Too.
How much alcohol is in this percent wise?
80, 90, something like that.
So you probably can't read that. But there's a clue. Okay, so look,
120.
there's a clue. Listen,
Not say 120.
Y'all.
That's a proof.
hold on. So there's a clue here. You probably can't read where it says what percent. It's some kind of little blip.
I think it says 65.
But it says 120 proof. Do you know what that means?
No.
Proof is double the percentage in an alcohol that you consume. So if it's
It's 60%.
60%. So the other percent is gonna be water and some other things. But
Yeah.
60% alcohol. So this is not an alcohol that anyone should be like sipping.
Yeah, is that safe?
So this is for mixing, but it's also can be used when you can pour this out on the counter and light it. You ever seen the bartender tricks where they make like fireballs, like they spit it, poof, and it like, they light their fireballs or those guys that perform that spit alcohol out and fire throwers, fire eaters or whatever.
That's not something you should be drinking.
No, not by itself, right? Mm-mm. Yeah.
That means you can use it in your
Yeah.
car's gas.
That's the next question. So it's grain alcohol. Its chemical name is ethanol. So he asks, can it make your car run? The answer,
Yes.
yes. Okay. Now, is it gonna make your car run efficiently or well?
No.
Probably not. But when you go to the gas station next time, look at the types of gas they offer. Most or a lot of the gas today, a gas station, excuse me, has some amount of ethanol added to the petroleum gasoline. Because it helps spread it out. It's less expensive because we're making this from corn. Like, that's real cheap, much cheaper than getting petroleum out of the ground, right? And refining it and all of that. So they mix it together. They started doing that, I want to say in the 80s, 90s. People used to call it corn squeezing. Corn squeezing, crappy ass, whatever. But the cars today are meant to run well on it. So there's some level of ethanol. So ethanol can be consumed. Ethanol is produced when you distill something, right? That's how you get distilled spirits. But when you do distilling, like when distilleries, like any of the ones we have some up in the mountains, the Jack Daniel's distillery, when they're making their liquor alcohol, there's also another alcohol, methanol, which you cannot drink. That will kill you, which gets mixed in, and you have to know how to get the methanol and the ethanol separated. And that's part of the distillation process. So a lot of the hand sanitizers that came out during the pandemic, when we were all like struggling to get hand sanitizer because there was a shortage, there were distilleries that started producing hand sanitizer. We got some. You probably got some. It smelled terrible. You're like, oh, it's like tequila or whatever. You know, I have one that literally smells like straight tequila, and it's not tequila, but it's the methanol that they have to dispose of, that they were like, oh, here's a use for this. People need hand sanitizer. So they put it out in hand sanitizer. Yeah.
Does that mean if I'm stuck on the road and on the off road and I found a gas in I found a bottle of Everclear one.
You could give it a try. It probably wouldn't work very well. But what you're looking for in our modern internal combustion engines is you're looking for something that spark can light and explode and move that cylinder. Remember when we did the paint can? So yes, it will work. It probably won't work beautifully, but it'll work. And ethanol, you ever seen the alcohol funny cars?
No.
The ones that race like super fast and have the parachutes off the back to stop them?
Yeah.
They're running on ethanol. Yeah. So ethanol looks like this. It's C2H5OH. That's your ethanol. All right. Which we will use next year. We'll use some ethanol and some methanol in lab. So yeah. Methanol is in like lighters and stuff too sometimes. So what's this?
Graphite.
Graphite. Everybody gets that one. All right. What's the chemical name for graphite?
Something.
So this is where we do one of those stupid things where we name something what it's not.
Clorox.
It's not actually, like in your pencil, we always say it's pencil lead.
It's like carbon.
It's not lead. Yeah, you're right, PJ. It's straight carbon.
And depending on the type of pencil you get, it could be more carbon and.
Right. So then what's the chemical formula for graphite? C. All right. So you got carbon and so basically graphite is just straight carbon, but it's not compacted all that tightly. You can rub it, as you write. But then you also have coal. What's coal made of? Carbon, but it's carbon that's been put under more pressure. And then what's this?
Carbon.
Yeah, a diamond is also straight carbon, right? It's just been put under a lot of pressure. So if you took your pencil lead out and like found some super duper pressure machine, you may get like a diamond in the end. Yeah. Oh, that,
I think I remember the Mythbusters episode where they were trying to make like diamonds out of peanut butter or something.
Oh, yes, I did see that.
What?
Yes, because it was videos that were going around the internet where people were like, we're gonna make a diamond in the peanut butter. And I'm like, this is so stupid. Yeah.
Mythbusters.
Yeah. I love Mythbusters.
It's such a good show.
No, it doesn't have nearly enough carbon to do it. Silly. So what's this?
Paper.
It's not paper.
Metal?
You might have used
Drywall.
this. Drywall. There you go. Where do you see drywall? Drywall. If your walls aren't plaster, they're drywall. Yeah. And then where the tape is, you get fun spots like this where it comes apart. Yeah, they put tape on them. There's a great video I've seen. Like that's you. You know the whiteout tape or the craft tape that you drag and it makes a nice line. So they actually have dispensers like that for drywall tape. Yeah. But you slap the plaster in it. And I saw a fabulous video of this guy. He like stuck it down and he pulled it and just went slap and it just sticks right to the wall with all the plaster for the drywall tape. It's really kind of cool. So what's drywall made of? What's our common name for it? Do you know?
Plaster?
Don't know?
Made of.
Plaster. She knows. She's thinking.
Right.
I'll help you. It's gypsum.
Oh.
Ah,
That's not common name. Common name.
drywall, yeah.
Gypsum.
Gypsum and drywall. You can also find gypsum that you can put out on your lawn. There's like, it's like a granulated gypsum. You can do that with it. It's for gardening or for putting like in potted plants sometimes. Yeah, granulated gypsum. You probably have some because your mother has every gardening thing on the planet, so it's possible. Yeah, so that's gypsum. This is a weird thing. About 20 or 30 years ago, the US got a whole bunch of drywall from China that is now it's now just known as like the Chinese drywall debacle. Because there was something in it, and I'm not sure what was in it, I can't remember, but whatever was in it was toxic. So people built like whole freaking houses with this stuff. My best friend's brother built a house with this drywall, and it was so bad that everything in the house had to go. Like it became a health hazard. You lost everything if you built a Chinese drywall house and then put your stuff in. No, it's not asbestos. I don't remember what was in it, but it was crazy. Asbestos, you can still find it in older houses, in tiles and insulation, things like that. And that should come out properly. Like you have to have trained people go in with the respirators and all and take it out. But of course, those of us who grew up in the 70s and 80s, like we were like eating asbestos and lead, and you know, that's why we are, that's why you can blame Gen X for being the weirdos that we are, because between eating lead and inhaling I remember my elementary school, like it was a big deal that we were leaving for the summer so they could take the asbestos out of the school. And that was in like 5th grade.
In the drywall, it was strontium sulfide.
There you go. Yeah, it was not good. So yeah, there you go. Like we'd all been in the school for 6, 7 years, whatever. And then they're gonna come in and get rid of all the asbestos that we've been living with forever. It was a big thing. Oh, we're gonna come back and the walls and the ceiling are gonna be, because all ceiling tiles are full of asbestos. Yeah, we're taking the poison out. Meanwhile, we've been breathing it. And then we got on this merry-go-round, so the playground that you run around, they throw you off. That's why we're all the way we are. If you wonder what's wrong with your parents, this is what's wrong with your parents. Like legitimately, that and we like rode on the armrests in our parents' cars with no seat belts. And yeah, this is why we are the way we are. So it's calcium sulfate dihydride. So who wants to give a stab to it?
No.
Calcium, PJ.
C S O, maybe a 2 because of the 8.
Two waters.
Shut up.
Shh, hang on.
2 the dot 2H.
Dot 2H2O. Okay, she's real close. There you go. So your SO is 4. If this is one of those ones, like carbonate is like CO3, sulfate is SO4. There's some that you're gonna use so much or see so much next year that you'll just know them. You'll just know what they are because you'll use them a lot. We'll use a lot of potassium chloride, sodium chloride, hydrogen sulfide. We'll use hydrochloric acid. We'll use sodium hydroxide. And these are all ones that you'll just learn. You'll just know what they are because you'll have used them so much. All right. Who's been to the dentist recently? Anybody know what goes in these? Yeah.
Laughing gas.
Laughing gas.
Oh.
Oh, anybody ever had it?
It's fun.
Was it a fun ride?
Yeah.
You had a fun ride too? So interesting biological fact. This isn't really anesthesia so much. I mean, it is, but it's not like general anesthesia, right? It's not like they're knocking you out. Do you know that we have an understanding of how anesthesia works, but not a really good one?
Oh,
Yes.
Like, we don't really get it. Meanwhile, we're knocking people out every day, you know. Uh-huh.
And like people with wet hair and gingers need more anesthesia.
Yes. Anybody have that gene?
What?
So if you have red hair, you may have, or like in my case, like I was born with red hair and it was red till I was about 1.5 years and it started changing. But I do have the gene, and I know I have the gene because people with red hair have a certain gene that metabolizes anesthesia way faster than your average Joe. So when I get even so much as my teeth numbed, when I go to the dentist, I have to tell, like I have a new dentist, I just got her a couple years ago, and I'm like, hey, I was born with red hair before we start this. And she's like, I got you. So I get stuck like 20 times and then they'll stop halfway through and stick me more because I will feel it. we'll be 5 minutes in and I'll be like, nope, nope, I feel it. Cause I metabolize it too quickly. I know, but a drill inside your tooth really hurts. I've felt the full thing before, cause I've had it completely be a situation where I'm like, there's a nerve, and you'll come out of the chair. Like, it is not fun. They got, you're good, you're chill.
Yeah.
But I'm like traumatized from it, so I get numb. The last time she did it so well, half of my face was numb for like 12 hours. Like, I came home and took a nap, I woke up, my eyes were still numb, I'm like, oh, but I would rather do that.
Yeah.
But so some people will metabolize it more, and that's a true thing. Like, anesthesiologists will straight up admit it now. If they're putting somebody with red hair under, they are monitoring more closely, they will give them more because they metabolize it more. But
So their bill is more.
yeah, right, it should be, you would think. So yes, this is laughing gas. Now, has anybody ever had one of those? You've had it? You said you had it? Was it a fun ride?
Yeah. My
Yeah.
dad just didn't have that.
It was a good ride.
I had a red mask.
You had a red mask?
I had bubble gum.
Did they give you the smell? Yeah, the smell, you can pick the smell.
I didn't get a smell.
It's so you don't smell the actual gas.
Pure gas.
It's
It's
got
not
that.
bad.
Yeah, it's not great.
Fun fact, if you're in a laughing gas for like, 1 week, you'll get 6 packs.
Oh, I'm sure, yeah, yeah.
6 packs.
6 packs.
What kind of YouTube ad?
I'm sure that's fun. The first time, I never had laughing gas as a kid, but when I was headed to the summer between my senior year of college senior year of high school and freshman year of college, I had my wisdom teeth out. And who's done that yet? Like,
I'm
you've
going-
done it,
I'm gonna have
you've done it. I thought, James, did
I'm
you?
going to.
Somebody back there did you get your wisdom teeth out? I thought one of y'all did. Yeah, oh, that's right. You didn't have them. That's right. So this was my first experience with this sort of thing, because I'm a very well-behaved person. At least I was a very well-behaved person. So they started the IV on me, and the nurse said to me, in a minute, you're gonna feel a little bit goofy, but she didn't get the second syllable of goofy out before I was like, oh. And I remember, like, then they left. They left me in a room by myself, and I'm looking around the room, and they had like a picture of the local ballpark on the wall, and I used to work there, and I'm like, I know that place. And then my leg fell off the chair. You know the dentist chairs, it's kind of like half bed, half chair. Well, my left leg fell off, and it's dangling off the chair, and I'm looking at it, and I cannot figure out how to get it back on the chair. Where it belongs. And I'm like, I don't know how to move it. So my genius was to grab it with my hands like this, my genius, and hoist my leg back onto the chair. And just then, the oral surgeon walked by with some random man, and they stopped and they looked in the room and they pointed and laughed at me. And then I fell asleep. But when I came back to get the sutures out, I was like, I don't think I was completely tripping. You were laughing at me. And he's like, oh yeah, that's the real estate agent. He lives next suite down. We have lunch together all the time. He comes over. He really enjoys what I do. I'm like, you got straight up laughing at me. I'm dangling. Like dangling.
They put me straight to sleep.
Did they?
Yeah.
Yeah. Well, I fell asleep after that and I was out, but I had a few minutes of, I'd never experienced anything like that in my life. And I felt safe because I was at a doctor's office. So I'm like, okay, I'm nothing bad's going to happen. I'm cool. But like, has anybody ever had morphine for any reason? Okay, they will give you morphine for extreme pain. So when I went in for my appendectomy, did you get it?
I think they gave me it because it was really painful.
Yeah.
I did not take it though.
Well, my problem with morphine is I'm one of those people that thinks they're having a heart attack and gonna die. That was not fun. That was not fun. Apparently it can cause extreme pressure and chest pain, but nobody told me this. She just injects my IV with morphine. Meanwhile, I'm like thinking I'm gonna die anyway because my appendix is about to explode. And I'm like, oh, and she comes and she like pumps this stuff into my IV. And I have like a list of drug allergies this long. So when I felt like immediate chest pressure, I seriously thought I was gonna have a heart attack and die. This is how I'm gonna die at the hospital for stupid appendicitis. This is how I'm gonna die. Like I panicked. And she was like, oh, it's okay. That happens sometimes. I'm like, you could have told me beforehand that there was a chance that I was gonna think I was gonna die. Honey, I'm gonna slide downstairs. So the chemical name for laughing gas is dinitrogen oxide. Anybody want to take a stab at that? PJ. So what is it? 2 nitrogen. So what's that going to be? N?
N2O.
N2O. Very good. All right. There's our laughing gas. All right. And everybody put a lime on their lawn?
Yep.
Lime. Yep. They used to, before they bothered to like paint, they paint football fields and soccer fields. It used to just be like this machine that would lay down a line of lime, and that's how they did it. We all crawled through that as kids too. Again, something else. So this is lime. What's the chemical name for lime?
Calcium and magnesium.
Calcium and magnesium. You see that right here. Supplies calcium and magnesium. So it's calcium oxide. So they've added some magnesium to the lime. So what's calcium oxide going to be?
CO.
CO? Think about it. You're close. What's calcium?
CaO.
CaO. We're thinking. All right. And look at that.
Doing carbon.
Yeah. Yep. All right. And then what's that?
Rock.
Pumice.
It's a rock.
The rock. It's not pumice. It's
Quartz.
Granite.
it's not granite.
Rock.
Ha! This is limestone.
Ah.
So we just said what lime was. Limestone is going to be very similar. So what do we think's in it? Calcium?
Zinc.
Calcium oxide.
Calcium oxide. Real close. Calcium carbonate. Okay.
Calcium carbonate.
There's that 8. So what's this one going to be? PJ, you want to take a stab at it? She's taking a stab.
CO.
Shh, hang on. PJ's turn. Go for it.
Answer.
Yeah, let her answer. Go for it.
CaCO3.
CaCO3, she says. Woo! She got it. That's the first one that or 2. I think we've got 2 that are solid so far. That weren't just like elements, just like carbon or sulfur. Real good. CaCO3. All right. So let's look at Lewis dot. So yeah, that's always fun. So Lewis dot structure. Here's how these work. These are pretty easy once you learn how to do them. And they can be helpful.
For nitrogen, we have 5 valence electrons, so we can put the N in the center to represent the nitrogen, with 5 dots around it. Those represent the valence electrons. Remember, valence electrons are the electrons that are involved in forming chemical bonds with other elements. That's why they're so important in chemistry. We can find the number of valence electrons using the periodic table. The group number tells us the number of valence electrons for the element. For example, hydrogen has 1 valence electron because it's in group 1, sometimes called 1A. If you look at group 2 or 2A, you'll see that those elements have 2 valence electrons. We'll skip over the transition metals since they're a bit more complicated and probably don't apply to you. We'll go to the 13 or 3A, which have 3 valence electrons, then 14 or 4A, each of those elements in group 14 or 4A have 4 valence electrons, all the way up to group 18 or 8A, which have 8 valence electrons. Nitrogen, which is in group 15 or 5A, has 5 valence electrons. So to draw the Lewis dot structure for nitrogen, we'll put the N with 5 valence electrons around it. So that's the Lewis dot structure for nitrogen. This is Dr. B, and thanks for watching.
Basically, you follow that same step for all the others. It's pretty straightforward. Yes.
Doesn't matter where you put dots, for example, here.
For nitrogen,
The dots is on the top, but.
It doesn't really. No. Mm-mm. Not really. Because what you're doing is you're trying to determine how many valence electrons so you can see how many are unpaired. Yeah.
There was a Professor Dave explain.
I know. I love Professor. There's so much Professor Dave explains in chemistry. Chemistry is like tons of Professor Dave explains because he's the best. All right. So an unshared pair, a lone pair, is a non-bonding pair of electrons in valence shell of an atom. And why isn't this clicking? Click, clicky, clicky. What's going on? Hello. Hello. And let's try it again. Hello. What? Okay. Okay. When 2 chlorine atoms form a covalent bond, each atom contributes 1 electron to a shared pair. So you can see here, I don't know what that's for, but this is your shared pair. And that's how you denote it with your Lewis dot. You see that? These 2 are being used here and here. So this is covalent. They're being shared. So what is a covalent bond in which 2 atoms share 1 pair of electrons? What was that?
Single bond?
Single bond, yeah, we had that earlier. That's it. It's a single bond. Very good. All right, and the electrons can pair in any order. However, any unpaired electrons are usually filled in to show how they form a covalent bond. So this is just your number of valence electrons, your number of bonds it can form, and an example. So if you have a hydrogen, it's got one valence electron. Then you've got your chlorine. How many valence electrons? 7. How many does it want? 8. Can it take one from hydrogen?
No, but maybe we can share.
Yeah, right here. They're gonna share it. There you go. All right, sample problem. So draw a Lewis dot structure for CH3I. So you draw each atom's Lewis dot structure, count the total number of valence electrons. So C, 1, 2, 3, 4, H, and then I. So your number of total dots you get is 14. So then you're going to arrange the structure so that the carbon is the central atom, like so, because that's just the way it works. And then, whoops, and then you'll know that way that you're getting a shared pair, a shared pair, a shared pair, and a shared pair all the way around that carbon, because it has the 4. These guys each have 1. Here's the 1 that's by itself, right? So it's this one and this one, for example, like that one and that one, right? All right, so when you're doing your nomenclature, you remember binomial nomenclature in biology, if you've done that, that's your genus and species, Homo sapien, for example, right? So this is nomenclature, which is how to name inorganic compounds. So it's just a flow chart. And we will work on this next year. We're doing a lot of this, but if you can kind of remember some of these steps, it'll help. And I won't expect you to like memorize a gazillion of these because it gets a little crazy, but it's good to know some of them. And like I said, some of them are just going to be very familiar because we'll be doing them a million times. So real quick, before you head out, I want to show you. Yep. Go away. Wow. Just wants to fight me. Wow. So just so you know, for our dance, we have a lot of tickets sold. We've got a whole bunch of folks come in. It's going to be good. We've got 30 some odd something already bought. So, whoops. May 10. It is. It's actually Drew's birthday.
Yeah.
We are celebrating Drew's 16th birthday with a dance. So it should be fun. If you where's the, oh, here it is. You can see if you have any friends on this list. Yes, it is very soon.
Oh.
So you've got, some of you are already on, what?
Yeah, that's next week.
Some of you are already on here.
It's next week.
Yep,
Yeah. Oh.
yep. It's next week,
Oh.
next Friday. So we got,
Oh, it's 2 weeks out.
yes, 2 weeks out. I'm sorry. Yeah. Rempe, Lamar, Maloney, Martin. Martin will be in class next year. There's some Rodriguez kids. Parker. For those of you who remember Parker, Morgan, some Cassim will be in class next year, I think. Berliner, I don't know. We got 2 McCoys. I think that is Jack.
Yeah.
And yes, Jack and Emma. Choppa Queen, we got Miss Emily here and a friend. I don't know who that is. We got Ridley. We got some Rollins. We got some Jolly kids, some Benson kids, and Samantha Black. No, Rollins. Although I think we may get Sawyer.
No.
Hayden's at National, so I think Sawyer's coming. I think he may. Well, Landon too. So I wanted to show you that. I also wanted to show you that if you go to our website, real quick, last thing. If you go to our website, to the calendar page, like, here's where we are, right? We are wrapping up right here. We're on 423. So we got class, and then exams and machine presentations, but your chemistry schedule is already up. So if you're here next year and you're wondering what we're doing, when we're doing it, and when you're off, it's already up. And do please note, there is some very weirdness in 4th quarter, just the way the schedule works out. You've got a spring break. That's the Forsyth County spring break, then a week, then a Holy Week break. I hate this. I wish they would always put it on one side or the other of Easter, but they don't. So that's going to be weird, but that's the way it's going to be because I cannot do that. I cannot do Holy Week. So you'll still get 2 weeks off, but there's a week in between. So I looked at maybe doing that class as an online class, but that is the class with the fun lab where we make bouncy balls.
Ooh.
We use chemistry to make our own bouncy balls, and that's a fun polymer lab, so I hate to make that online. Any questions about this week before you head out? You're good to go? All right, and we will see you next week, gang. Come get your coins.
I wanted to ask what I don't need it when I show up next week, you'll work on it because basically everything